Hello and welcome to another Physimathizer video. Today we're gonna try to find the general formula for the integral of an inverse function f inverse of x, as well as a general formula for the definite integral of the inverse function of x. And we're going to try to use our newly found knowledge to evaluate the integral from 0 to 1 of the square root of negative ln of x dx. Well, let's start by looking at the graph of the inverse function f inverse of x. Notice that this is the same as the graph of the regular function f of x. It's just inverted around the line y is equal to x. So the thing we're interested in here is the integral from a up to b of f inverse of x. This will just be the area shaded in green. And so this will just be also equivalent to the area between the y-axis and the graph of the regular function between the values of y is equal to a and the value y is equal to b. Well, at the value of y is equal to a, the intersection between this line and the graph of the function f of x happens at a value of x is equal to f inverse of a, since f of f inverse of a is just a, and the same is also true for b, so the value of x here is f inverse of b. And so the green area between the graph of the function and the y-axis is actually equal to the area of the yellow rectangle, subtracting from it the red area under the curve, and also subtracting from it the purple area, which is itself the area of the blue rectangle, subtracting from it the dark green area under the curve. Well, this just simplifies to our integral being the area of the yellow rectangle minus the area of the rectangle. This is b times f inverse of b, since the height of the rectangle is b and its length is f inverse of b, subtracting from it the integral from 0 to f inverse of b of f of x dx, which is just the red area under the curve. And then we subtract from it the area of the purple part, which is itself just the area of the blue rectangle, a times f inverse of a, just like we had with the b times f inverse of b, minus the green area under the curve, which is the integral from 0 to f inverse of a of f of x dx. Well, rewriting this becomes the integral from a to b of f inverse of x dx is just equal to b times f inverse of b minus the integral from 0 to f inverse of b of f of x dx minus, between parentheses, a times f inverse of a minus the integral from 0 to f inverse of a of f of x dx, and simplifying this becomes b times f inverse of b minus a times f inverse of a, and I merged the two integrals here to become the integral from f inverse of a to f inverse of b of f of x dx. Well, this is just our formula for the definite integral, and so our formula for the indefinite integral is what we get by trying to find the thing with which, when we evaluate at two different inputs b and a and subtract them from each other, we get our formula for the definite integral. Well, what is this thing that when we evaluate at two different values gets us the definite integral? Is just the definite integral which will be equal to x times f inverse of x minus the antiderivative of the regular function evaluated at the value f inverse of x, which is just to say that the indefinite integral of f inverse of x dx is just equal to x times f inverse of x minus an antiderivative of the regular function evaluated at the inverse function. Well, let's put this knowledge to the test by trying to find the integral of the inverse tangent of x. Well, by our formula, this is just x times the inverse function minus the antiderivative evaluated at the inverse function. Well, this would just be x times the inverse tangent plus the logarithm of cosine of the inverse tangent plus c, since the antiderivative of tangent is negative log of cosine. Two negatives cancel each other out, and the thing inside the cosine is just as we said, the inverse function. That's where we evaluate our antiderivative at. And so that's just our formula. Now I'm going to try to simplify the thing inside the logarithm a bit. We start by imagining we have a right triangle with an angle whose tangent is equal to x over 1. And so the hypotenuse of this right triangle will be equal to the square root of x squared plus 1 by the Pythagorean theorem. And so the cosine of this angle will just be 1 over the square root of x squared plus 1. And so the thing inside the logarithm is just 1 over the square root of 1 plus x squared, which is 1 plus x squared to the power of negative 1/2. And so we can rewrite this whole thing as x times the inverse tangent of x minus a half the logarithm of 1 plus x squared plus c. I've just taken the power to the negative 1/2 from inside the logarithm to the outside. That's just done by our usual logarithm rules. And we don't forget the constant of integration at the end. In this formula is indeed the antiderivative of the inverse tangent, and you can find it just by integration by parts, but here I have used our formula for the inverse function just to check its validity. Here we needed to put it to the test on something we know. Well, now let's put it to this test on something we don't know, which is the integral from 0 to 1 of the square root of negative log of x dx. Well, the thing here inside the integral is our inverse function. So first thing we do is try to find the regular function, which we do by replacing x's with y's and trying to solve for y. This means x squared is equal to negative log of y, negative x squared is equal to log of y, and so y is equal to e to the negative x squared, which is just the Gaussian function, which is a really popular function that pops up all over probability statistics and physics. Well, now we using our formula for the definite integral, we see that this integral from 0 to 1 of the square root of negative log of x dx will just be equal to 1 times the square root of negative log of 1 minus 0 times the square root of negative log of 0 minus the integral between the square root of negative log of 0 up to the square root of negative log of 1 of e to the negative x squared dx. And bear with me a second, I know this 0 times the square root of negative log of 0 looks weird, and it is indeed just 0, since if you consider the function x times the square root of negative log of x, indeed the log of x approaches negative infinity as x goes to 0, but x also approaches 0 as x goes to 0, and x approaches 0 much faster than the square root of its logarithm approaches infinity. And so this is indeed 0 times something that approaches infinity much slower than 0, which is just 0. And so our integral is just equal to the integral from 0 to infinity of e to the negative x squared dx, which is just the square root of pi over 2. Well, the integral from 0 to infinity of e to the negative x squared dx is just called the Gaussian integral, which you can look up on YouTube. It's the really famous integral. And what we did now is just replace our odd weird integral with a much more familiar one. Indeed, you can solve this integral in many other ways, but using our formula is slightly easier and definitely gives you more insight as to why the value becomes the square root of pi over 2. It gives you insight that other methods won't give you. You'll just wind up with this answer not knowing where it came from. Well, if you like the video, don't forget to like and subscribe. And until next time, go Physimathize the world.